Hello, everyone, and welcome to the fifth session of our online seminar on optimization. I have the pleasure to introduce today's speaker, Alberto Domínguez from Universidad Graz in Austria, and he will tell us about invariance theory in Wasserstein spaces. So, Alberto, please.
Hi, it's a pleasure to be here, and I would like to ask if, no, I will ask in Spanish. No, how is it? Is there anyone who cannot speak Spanish?
I think Matías,
Yeah, probably.
probably.
So, English or Spanish? How do we?
Just in case, we should stick to English.
English.
If you want.
Okay, let's do English.
Thank you.
Let's go. Well, I want to talk about invariance theory in the space of probability measures and mean field dynamics. Um, in order to discuss all of these things, I will try to break these topics into several parts. I will talk first on what I mean by invariance theory. Then I will talk about what its mean field. Then I will talk about what the space of probability measure is. And finally, I will try to combine all of these things together. Well, first, let's start with the what invariance in the Euclidean spaces. Here, there is an animation, and there is a particle moving by means of a ordinary differential equation. The interesting thing about this is that the region, which is drawn there in the black, contains the whole trajectory of the particle. The particle never leaves the trajectory. Whenever a dynamical system satisfies that an initial condition given on a set, the trajectory remains for the whole time inside the set. We refer to this as invariance of sets, hence the name invariance theory. Mathematically, it's something like this for the particular case of ordinary differential equations dynamics. A set Q is said to be invariant for a system if for every initial condition x sub 0, the solution belongs to the set Q for all times. I mean, it never escapes the set. So one can say that the dynamics, it's invariant. One interesting thing about this is, for example, here there's an animation. On the left-hand side, you can see that the trajectory never touches the boundary. It moves in the interior of the region. Intuitively, one can think that whenever we give an initial condition in the interior of a set, one does not have to worry of this particle leaving this region so quick, right? Because if the trajectory is continuous, at least for a small ball, the trajectory cannot escape the region, because there will exist a small neighborhood in which the trajectory remains inside this neighborhood. So somehow interior points are not of interest in the theory of invariance for continuous trajectories. On the right-hand side, you can see a trajectory which does touch the boundary. And the important thing is that when it touches the boundary, it goes tangent together with the boundary. This allows for the particle not to escape the region. And this is the most important observation that one can make in this theory to relate dynamical systems to the geometry of objects, the geometric regions. Well, let me say that, for example, if you have a trajectory over a manifold, it will be invariant if and only if the vector field of these dynamics, the velocity at every point, belongs to the tangent space. This is more or less implicitly assumed in when topologists define what a manifold is, because they say whenever they define a dynamical system, the vector field, it's always defined from the manifold to the tangent space, to the tangent bundle. So implicitly, they already know that for a dynamical system to make sense, they have to define it in such a way that the vectors field belong to the tangent space. You can see it, for example, if you have a trajectory over a circle, that if you do not follow the tangent space, you will easily leave the circle, right? This is intuitively obvious. Here, for example, I have a sphere. It's clear that if you follow any other direction, you will leave the region. So with manifolds, it's very easy, right? But with the pass of years, people became interested in more complicated regions to study invariance. And these regions might not be smooth. So they came up with a notion to generalize these things. This is the so-called tangent cone. Just let me give quick reminder of, I will not go into the mathematics deeply, but essentially the tangent cone has all the directions which are tangent or inwards the cone, or the region, sorry. It's some type of generalization of the tangent cone. It's a non-smooth, it's an object to deal with non-smooth sets. Of course, if you have a set which is already an immersed smooth manifold, then the tangent cone will coincide with the tangent space. So, I mean, this is a generalization of smooth manifolds in some sense, right? And instead of discussing the definition, I will discuss some examples. For example, these two. You can see to the right a region which is convex, and you can see the tangent line, the supporting plane, the supporting line. The tangent cone of this will include all the tangent directions and all directions pointing inwards the set. This is important, and it's good to study invariance, because you can see that if your particle goes to the boundary, you don't really care if it bounces, if it comes inwards the set, because if it comes inwards the set, you don't care, you are not worried, it will escape. So having inward directions, tangent directions is fine. Here it's a more interesting object. The right-hand side is a non-smooth region. You can see there are cusps, for example, here, but the tangent cone captures all inwards directions and tangent ones, even for non-smooth objects, as you can see here on this picture. Good. Okay, we have a generalization of tangent space. And the interest of this object is the so-called Oban theorem, which establishes that a set Q is invariant for a dynamical system driven by an ODE if and only if, I mean, for every initial condition, the whole trajectory will belong to the region, if and only if the vector field belongs to the tangent cone for all points, right? This is intuitively, this makes sense. Of course, the theorem is not so easy as these geometrical pictures, because this holds for arbitrary dimension. It's particularly useful for other things. Tangent cones are not always geometric. This is more This is a theorem that it's indeed helpful to characterize other conditions for different purposes. Like instead of particles, one can consider agents and so on. Classic bibliography for this is the book of Oban, as I said, the book of Oban and Frankowska on set-value analysis, and for sure, the book of Clark, right? In not smooth analysis. Okay, so this was the first part, and it talking about viability theory, invariance theory. Now I want to talk about other thing. This is the so-called mean field limits, which have become very popular in the past years. Okay, to the left, there are some particles moving. There is a dynamical system of several particles. If there are not so many particles, one can still do some calculations, right? One can calculate the dynamics, put it into the computer, and see what happens. Making theory becomes complicated when there are several particles, but still one can do some computations. But if we increase the number of particles, then it becomes problematic even to do computations, right? If there are too many particles, the computer will not be able to handle such much complexity. This is where the so-called mean field limits come into play. Instead of modeling the dynamics of many particles, their statistical behavior is considered. This is useful when one considers multi-agent systems consisting of a large numbers of agents, and for example also in particles and so on. For example, here is another animation. This is for pedestrian flow. Imagine that you go to see a movie. There is a door and it's usually not so big, so when everyone wants to leave, they all go together to the door, right? Of course, if there are a few agents, a few people, they will be able to leave the cinema room easily. But if there are many, 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 it starts to become complicated to leave the room, right? And mathematicians somehow want to make also statements when there are many, many agents, right? Though computations are very limited when there are many agents. This leads to the mean field. Okay, well, now some mathematics. The dynamics are modeled by differential equations. You can think of it maybe like a Newtonian way, but not in general only Newtonian, right? There many systems may arise. And then each agent has an equation, and the velocity field, it's not only affected by the agent itself, but it involves the action of all other agents. Here you can see the formula. In order to do this mean field approximation, one needs to make some consistency assumptions with respect to the symmetry, right? It's clear in the example of the theater, or the movie theater, that all agents should be indistinguishable in the sense that it does not matter if one has a red shirt and the other a green one. They are all agents, and if I swap their positions, the problem continues to be the same. This is captured mathematically by permutations. You see, this means that one can interchange the agents and the dynamics will not change, right? This is an assumption which is consistent with many applications. And also it allows to consider statistical approximations. Let me give some examples of what I mean by these velocity fields. For example, there are models for the interaction of particles, of attraction, repulsion. Most of them come as a sum, and it's clear that under permutations they do not change. Here's another model. This is for flocking. Maybe you have seen on the sky that the birds all together make a specific shape, and this can be modeled. The many birds or many fish start to make shapes, and they usually are very geometric. So this is modeled by Cocker's male kernel. All right. So we have a dynamical system. We have to study many agents, but we said it's hard to do this. So what one does is to do a statistical approximation. Instead of thinking of all of the agents, we start to consider the empirical distribution, How many agents are there per regions? You give a region and you can say the percentage of agents in this region. Statistically, it's easier to think, just take empirical distribution, just statistically how it behaves. This popular measure, the empirical density. I might not know the trajectories, but I can still think that if I knew the trajectories, I will know this empirical measure. I do know that if I add more particles, they will satisfy some equations. So theoretically, I can continue to add and increase the number of agents, even if I don't know the trajectories. Because I don't know the trajectories, I don't know the empirical density, but I can play still with it and add more agents and then take limit. And after taking the limit, I will not know what is the limit because I don't know the empirical densities. But one thing that I will know is that it has to satisfy some equation. So what I do is just take the limit, find the equation it should satisfy, and then solve this new equation. I cannot solve my system of equations, the original system, but I will solve the limit of these empirical densities. What am I? Yeah. This leads to a conservation equation. It leads to the continuity equation, which is here. This equation is understood in a very weak sense, the sense of distributions. It's not really relevant for this talk, all this analysis, but it's important to have this in mind. You will have some equation. You will replace your dynamics by some equation, which only depends on a measure. And this will, of course, model many agents, right? Because I took limit as n goes to infinity. Here is a picture to illustrate this behavior. On the left-hand side, we start with a few particles. Each of them have a velocity field, that determines how they move. I start to increase the number of particles, starts to become harder, but I do statistical approximation of them. Then I take the limit, and then I see the evolution of a measure over time. So from now on, I forget my dynamical system of differential equations to consider only one partial differential equation, whose solution is a measure indicating the statistical behavior of our particles or agents, depending on the model. Of course, there are many good references. I put here a few. The classical one by Lyons. But there are many books. I mean, you just can Google mean field and you will see that there are too much literature nowadays on this. Okay, perfect. So before I talk about invariance in the Euclidean space, I had trajectories in the Euclidean space, but it was very hard to analyze these trajectories in the Euclidean space. So what I did was to replace these trajectories by a simple evolution of a measure, right? But this creates a new problem then. If I want to study invariance, now I have to do it in the space of probability measures rather in the Euclidean space. And then I have to think, okay, the space of probability measures is complicated because it's not even a linear space, you know? It's a subset of many linear spaces. What is the right topology? There are many topologies in the space of probability measures, you know? But we will use the so-called Wasserstein distance. Okay, just a few notation. The space of probability measures with finite second moment is usually this denoted as P sub 2. This space has a natural distance, which is based on optimal transport. I will not go very much into optimal transport, but it's essentially the moving of the densities. You can think of density as a bunch of sand, and this distance measures the best way that one can transport sand piles from one distribution to another. I mean, there is a lot of theory about this, but I will not go in detail. But it's a well-studied theory. I mean, there are many tools in optimal transport to understand this distance. Essentially, it measures the optimal way to move a pile of sand. I mean, just think it. Imagine you have a lot of cans, right? Put them all together as a pyramid. You know, it will look like a histogram. Or what is the optimal way to move it into another pile of cans? Like in the supermarkets where they put a lot of cans, making like a pyramid and so on. Well, optimal transport answers this. Okay, so the most successful view in the space of probability measures has been so far the pseudo-Riemannian interpretation of it. Instead of thinking the space of probability measures as a subset of a linear space, one thinks this space as a manifold. And in order to do this, one needs to define tangent spaces. One needs to define what differentiability means. Of course, this is complicated because there is no linear structure. So what one does is to use absolute continuity, because since the space of probability measures with the Wasserstein distance is a metric space, it is possible to define what absolute continuity is. This is defined here is if you were in a Hilbert space, this would coincide with the usual definition of absolute continuity. One can also define non-smooth objects as a metric derivative, which essentially it's a measurement similar to what one understands as speed, right? We might not have velocity, but we can intuitively have a rate of change, the speed. Okay. But of course, I mean, with the speed, you cannot define structures, right? It's fine, and it's good to have this definition because whatever we define should be consistent with this speed. But it's not enough to define velocity. This was solved by, if I remember correct, I mean, this was the idea of Otto, but it was Nicola Gigli, the first one who proved this. And the idea is very simple. If you have an absolutely continuous curve, well, you don't have a derivative, but you can find a velocity field such that this curve satisfies the continuity equation. So far, this is trivial, right? You can always find velocity fields, but there is a very special velocity field one can find, you know, and one can find a velocity field such that its L2 norm taken with respect to this measure coincides with the speed the metric speed, the metric derivative. So the common interpretation is this: take your absolutely continuous curve. You can prove it satisfies the continuity equation for some velocity field satisfying this. So this velocity field will be identified as the derivative of this curve mu. It's a little bit unorthodox, but this has been working for many purposes in the theory. Of course, with this identification, Otto was able to define many things, in particularly tangent spaces, a metric tensor. This allows to think of space of probability measures as something that looks like a Riemannian manifold. It's not a Riemannian manifold. It has been proved that there is no Hilbert space, that you cannot take a point and expect that locally your space of probability measures look like a Hilbert space. This is not, it's known that it's not possible, but still you can still think it as a manifold. Because you have a metric tensor, right? And this is what you use in Riemannian manifolds. Good. Okay, this space is interesting. It has a lot of geometry. For example, one has actually geodesics, and these geodesics are determined by optimal transport mappings. So it connects very well with the interesting things in optimal transport. It has physical interpretations depending on the problems. And having geodesics allows to define the exponential mapping in a manifold. And this will be important for us because we want to study the invariance theory. And you know that the exponential map, it's a good substitute for many objects that are flat. Of course, if you have a geodesic, you can express it as an exponential. Okay. And the classic references for the Wasserstein distance are the book of Villani, and one of the classics that it has become a Bible, though it's very hard to read. It's the book of Ambrosio, Gigli, and Savary, Gradient Flows in the Matrices. And my favorite, the paper of Otto, The Geometry of Dissipative Evolution Equations. These papers contains all the ideas from which the book of Ambrosio was written. It's a brilliant paper. It's totally a breakthrough. Okay, good. Okay. So far, I have talked about invariance theory in the Euclidean space, mean field limits, and the Wasserstein space. So now I want to talk about what I have been doing in the past year, which is try to understand these models. I want to study the invariance in the Euclidean space, but I have systems of particles which are too big to be understood by standard methods. So I use mean field. But the problem of the mean field is that it takes me to the space of probability measures, which has a certainly more complicated geometry. But okay, once I get to this space, I might be interested to understand the invariance of some statistical properties for these mean field models. For example, I might want to have an initial distribution of agents, which is maybe has bounded variance, bounded second moment. And I'm interested in that during the evolution of this system, the moment does not go further than this, I don't want the system to explode the variance, for example. I might want to have, my agents in a certain region. This can be understood statistically as having the support of the measure, contained in some set. And I might want to have to find sufficient and necessary conditions for the evolution of this continuity equation to preserve the support. Here there is an animation. of a Gaussian measure, evolving from one with high variance to one with lower variance, right? Of course, one can think of many applications of driving systems to reduce variance. Okay, here now is the most important thing. In order to do invariance theory in the space of probability measures, in order to replicate the theory of Oban in the Euclidean space, I need a tangent cone, a geometric object to relate these things. And what one does is taking advantage of the geodesic structure of the Wasserstein space, and one defines a tangent cone identically as in the Euclidean case, but now using the Wasserstein distance and the exponential mapping. And this is the substitute, and it turns to work quite good. Okay, the main interest of this theory would be to recover the theorem of Oban. But before going to the theorem, I want to give some examples so that this is not too crazy, right? Because this object seems not so conventional. So first example, imagine that the set you are interested in is the probability measures such that the support is contained on a closed convex set, right? Imagine all your agents, and statistically you want that your agents do not leave certain region, right? So you will be interested in that the support does not, that your trajectory does not, the support of your trajectory does not abandon this set. And when you calculate the tangent cone, you realize that this tangent cone is consistent with the Euclidean one, because it will give you all the directions such that satisfy the Oban condition in the Euclidean sense. I mean, so you recover the usual tangent cone in the Euclidean space, right? What you need is that your velocity field, mu almost everywhere, belongs to the tangent cone of the Euclidean set. Another example, which is of interest, is the fixed mean constraint, right? You might have an initial distribution with certain mean expected, you can think of this as random variables also, that the expected value is fixed. So once the continuity equation does not respect the means, one needs an extra condition for this, and doing some calculations, one can check that the tangent cone, it's precisely the velocity fields that satisfies this orthogonality condition with the measure. So you see, if you had a system of agents, you will try to impose these conditions by means of some controller or something. Okay, of course, there are other examples. For example, you might want to start with a density, and you do not want your continuity equation to convert your dynamics into something which is not absolutely continuous, right? It can explode in finite time. So one can put restrictions. One can calculate the tangent cone, but it's much more complicated in general. It's easier if one fixes a density and then calculates the cone for this particular density. Another example is that if you start with a Gaussian distribution, you might want the continuity equation to preserve this. But the tangent cone shows that in order to preserve the continuity equation to preserve this, you will have to have affine velocity fields. It's very hard to conserve Gaussian measures. You need affine velocity fields. They do not behave very well under nonlinear transportation. Okay. I will finish soon. But the main idea of all this talk is the following. There is some motivation from mean field limits to consider dynamics which are measure valued and are driven by the continuity equation. And in this sense, one can also define what invariance means. And a set Q is said to be invariant for a dynamical system, like the continuity equation, if for every initial measure, every initial condition, your solution will remain inside this set. We already discussed there are many interesting sets: fixed mean, fixed support, bounded variance, absolutely continuous densities, Gaussians, and so on. There is some interest in this. Now the big question is, can we recover the Aubin theorem? The answer is yes. And here is the theorem, which is a set is invariant if and only if your velocity field that now depends on a measure belongs to this tangent space that we define. You know, you remember this tangent space in which the exponential mapping in the Wasserstein space is used. So yeah, the theorem can be recovered under some assumptions that are okay when one considers limits of mean field problems. And this was proven first under some conditions by Hélène Frankowska and Benoit Bonnet in the Wasserstein space, P Wasserstein, with some Lipschitz assumptions in the velocity fields. And it was then we worked afterwards in the theory in the one Wasserstein space, because somehow the one Wasserstein space is more natural for these things. As you know, in the ODE case, the natural space is L1. But of course, you know, the W2 space, it's easier because there are more geometric objects available. When one works with the one Wasserstein space, things become much more technical because there are many things that are not that break, you know, some geometric objects break. So we work on this, and we also work in the minimal regularity for the velocity fields with respect to the measure, and we got a sharp result. Instead of assuming Lipschitzness of the velocity field, one assumes upper semi-continuity. But these are technical details. I mean, what I wanted to communicate is that you can recover the theory of invariance in the space of probability measures. And essentially, that's all I want to say. And I will finish with this theorem.
Well, Alberto, thank you very much for this very nice talk on a very interesting topic. So if there are any questions, we have some time. So let's see. Emilio?
Thank you very much, Alberto, for the nice talk. I have a small comment. When you read the book of Oban, he said that the theorem is due to Nagumo.
Ah, this is true. Yes, yes, no, yes, this is true.
Oh, and,
This
and
is true.
also and also he wrote something that for me was very nice because he said Nagumo theorem was proved 17 times, but that's not implied that is true. and he proved again.
No,
So
it's correct. But this is called the Oban theorem because here it's written, I wrote it for a function, a local Lipschitz function. But Nagumo wrote it for a function, not for a set valued mapping.
okay,
So what Oban did was to prove it for a set valued mapping. And then the people started to call it Oban theorem. This
okay,
is totally true. Nagumo wrote it for the first time in the context of Lyapunov stability. I do not remember very well. But yeah, it's true. Nagumo did it for single valued functions.
okay,
It should be
okay.
the Nagumo-Oban theorem. You're right.
Yes, yes. No, because in general I use it as Nagumo. Uh, and another, I have a question because there are very nice paper about from Plaskax in Frankowskas where they work with the case where the set Q depends on time. So
Ah, yes, in our paper, the set Q depends on time. You know, in the paper of, let me go. In this first paper by Helen, the the set does not depend on time, but in our new paper, it depends on time.
I see.
But this makes the analysis even more complicated.
Yeah, yeah. And what about the assumptions about the multi-valued function of B?
Well, here, okay, here I have single valued, right? But for the multi-valued, in the paper of the first paper of Len, it's Lipschitzness with respect to the measure.
Mhm.
But in our new paper, it's upper semi-continuity with respect to the measure. You know, you put the topology of the Wasserstein space in the domain of this
Mhm.
velocity field, but you put the compact open topology in the codomain,
But
and you ask for upper semi-continuity
in both variables.
only in the mu variable, the measure value variable.
I see. And okay. But what about do you have this notion of weak invariance, stroke invariance, or because when you work with without uniqueness, you have to decide if you work with weak or strong invariance.
We call it viability if there exists at least one, and
Okay.
we call it invariance if all of them. Actually, it's not. I mean, you know that if you do the proof for one, then more or less the proof for the other is the same. Uh, so we did the paper for viability. There exists at least one.
I see. I see.
Yeah.
So I see we have more questions in the audience.
Hello.
Hey,
Thank
how
you.
are you?
I'm good. How are you, man?
I remember we met in Portugal.
Well, Porto, see.
I remember.
A very nice talk. Thank you for this presentation. I just have a couple of questions regarding the viability and I mean, I think it's the weak invariance in this case, since
Yeah.
you prove existence of a trajectory. My question is, since the inspiration is the mean field limit, does your theorem allow for like trajectories that allow division of mass? Like because for example, if you start from a measure that's not absolutely continuous and you want to go to another measure, target measure, sometimes you don't have an optimal transport map, but you have an optimal transport plan. So you want to allow like the division of the mass. So my question is, if in the theorem, do you include those trajectories also? Does it work for any trajectory?
It only works for trajectories that satisfy the continuity equation. I mean,
Okay. Well, all trajectories satisfy that. Like almost if, in the distributional sense.
yeah.
So
But yeah. But
okay.
I mean, the question. I mean, what is exactly the question? I mean, you fix.
Uh,
You have some initial measure, and the velocity
yeah.
field. This is fixed. Aha.
Yes.
And
Mhm.
you mean if you want to put a set that does not allow the splitting of mass over time,
No. It's like, for example, if you let's say you start from like an atomic measure. Okay.
correct?
If you want to start from an
And
atomic
you will
measure.
stay forever. If you start with an atomic measure,
Uh-huh.
the the continuity equation will not allow you to transition to density in finite time.
Okay, so that's my question. So you cannot like split or
Yeah, no,
regroup the mass.
no,
Okay,
no,
so those trajectories are not allowed in this setting.
no. In this, no. I mean, this is the nature of the continuity equation.
Oh, okay. Okay. I mean, in general, since the space is geodesic, you can go, technically speaking, from an atomic measure to a density through a
No,
geodesic.
yes, you can, but not by the continuity equation style. No. Not
Yes,
under
I
the
mean,
assumption.
exactly. You wouldn't have like the upper semi-continuity of the vector field of or the Lipschitz continuity for that matter. So that was my question. Okay,
Yeah.
thank you. Again, it's a very nice talk. Thank you.
Nice to see you, man.
Nice to see you too.
So Christopher has a question.
Yeah, just I think it's more or less in the well. Thank you for the talk again. It's related to what Odmen was asking because I think the point is that okay, actually with the continuity education you can have this splitting of masses behavior, but the point is that here you are taking B to be Lipschitz, so that
Yes, and there is some
doesn't allow
Lipschitz.
you to have that. So, but in general you may have something. I mean, from and no, I think Emilio already asked what I wanted to ask, but just to check it, in your paper you are you are studying just a vector field and a set, and then you say you have the invariance. You don't put the question about a strong invariance or weak invariance or what Ovan's called viability or invariance. You don't focus on that in the paper, right? Can you hear me? Sorry.
But you asked this to Emilio, right?
No, to you.
Sorry, what was the question? I thought you asked him.
No, I was following Emilio's. So in your paper, you did the invariance, just invariance, like like Nagumo's theorem is just for an ODE. So in your case, you don't have many choices for the vector fields. This is
In the paper, we did something like exists a solution, weak invariance, and yeah.
okay. But you don't have, for instance, a choice of possibilities for the F, for the vector field, such that you
No,
have
yes, no, you have. In the paper, the vector field is set valued mapping. There are
Okay. So, but okay. So in the paper, how do you get at the end the condition? Because at the end, the theorem you show.
okay, I understand. Yeah. I mean, I didn't want to put set valued mappings because I thought that for a talk, maybe it's too much,
Yeah,
but
no, just to understand. I mean,
what
because
you get here, it's that the tangent cone intersects the set valued mapping. Yeah. You get here intersection of the set valued mapping with the cone. In the case that the set does not depend on time.
yeah, but here you have to know the measure mu, because you are evaluating the tangent cone at mu, if I understand correctly. Because in general, what you have in invariance is that you have a vector field, let's say B in Rn. You have B that depends on X, and that the condition you said that that vector field belongs to the tangent cone to the set at X. But you don't have a reference trajectory already. Then you construct the trajectory. But here it seems to me that the way you're writing the theorem seems to me that like the trajectory and then you say
No.
this is
This
the
is actually
condition.
this is a typo. It should V of mu belongs to T sub Q of mu. I put T because I copied some slide. No, you're right.
Okay, so it's okay.
Yeah, it's true. I made let me go to the original one. Yeah, there is a slight mistake.
You already passed it. Yeah, that
Yeah.
one. Yeah.
E of x, yeah, it's correct for all x. But what you have to put, you don't know the trajectory. You don't know it. What it should be here, it's without the t comma point. It should be
Okay.
just b that depends on mu belongs to t of q that depends only on mu. Does not depend on t. This is something
Okay, but somehow, so you are in. Okay, so at the end, your vector field belongs to the continuous functions, but your tangent cone space is in L2, so it's much bigger. Okay. So.
Yes. It's much bigger, the tangent cone, because it has L2. And this is restricted to continuous.
Okay. Okay, thank you.
Yes.
Are there any more questions? If not, I would like to ask something, Alberto. So I think
Yes.
at the end you mentioned that in your latest paper, you work on the Wasserstein 1 space. And I think
Yes.
you said that it was somehow easier or more convenient, which sounds very strange to me because I
No,
would.
no, no. I'm saying when you study, for example, the theory of ODEs,
Mhm.
you realize that the natural space to obtain the weakest is L1, right?
Yeah.
You can prove that your solution is in W11, exactly, which means absolutely continuous. And you can get all the theorems with this. You don't use W212, you don't use the Sobolev space H1 because you work with integrable derivative, which is integrable. So when you study these dynamical systems, the analogous is the W1, but the W1 is more complicated than the W2. Saying that for ODEs, W1 is of course much more difficult than that L2, right? L1, it's a terrible space. It does not have the Radon-Nikodym property. It does not have the Aslum property. It has nothing. It's not the dual of any space. It's problematic space. So, but it's still the natural space. Everything seems to be related to this space when you study ODEs. You know, so this is why we wanted to do it for the W1 space because some things are much more natural, but there is some cost that topologically is very bad.
I see. So I imagine that some of these somewhat Riemannian tools that you had for W2, maybe they don't work anymore in W1, right?
This is correct. For example,
You don't have a metric tensor, maybe.
I said that the key is to have a velocity is that for every curve, which is absolutely continuous, there will exist a velocity field such that this is satisfied, right?
Mhm.
This is not true if you are in W1. You cannot have this in L1. So you break this theorem. And this is very bad, no? Because this was the differential structure idea. But you still have geodesics. So, okay, maybe you lose this, but you have geodesics in the W1.
Yeah. Okay, thank you very much once again, Alberto, for this very nice talk.
Thank you for inviting me. It's
Thank you very much, Alberto. Nice to meet you.
nice to meet you.
Bye bye.
Bye, everyone.
Bye.